We know that a normally distributed population is going to have a bell-shaped curve. It's going to be symmetrical. The mean is going to be in the middle. Okay, mu representing the mean for the population. It's going to have a distribution that's represented by a variability that can be measured using a standard deviation. In this case, I'm going to call the mean 100. We call the standard deviation 10. Okay, so we know that in a standard normal distribution, okay, that within two standard deviations of the mean, below and above the mean, okay, -2, +2, that we have approximately 95% of the values for that population. Okay, some population is going to be wide and narrow, wide and spread out. Still going to be, since it's spread out, the standard deviation this time is going to be bigger, right? But it'll still have the same characteristic, two standard deviations to the left and the right. In this case, that would be 10, then 100. This would be 80 to 120. In this case, it would be 60 to 140 if the mean is 100 and the standard deviation is 20. We know that that's roughly the case. We also know that in reality, this standard normal distribution is represented by a fairly complex formula based on chance, the chance of getting a value less than or greater than the mean, and that in reality, that 95% of the distribution is really not quite -2 and +2 standard deviations, really negative 1.96 standard deviations and positive 1.96 standard deviations above and below the mean would represent 95% of that population. Okay, so now we say to ourselves, well, gee, what about all the other values here? What percentage of the values are 1.5 standard deviations below the mean? What does this area represent? How many people out of that entire population, or how many values does that represent as a percentage of the entire population? Well, we know we use a z-table in order to evaluate that. I'm going to see if I can't find that here in the background. Okay, I have a copy of z-table here. Okay, here's a z-table. And we can see that if the z-score is -1.5, this table tells us that in this table we can identify what the area of that proportion of the standard normal distribution that would be represented below that value. Okay, so -1.5, it would represent -1.50 would be represented by about 6.68% of the distribution below that value. About 6.7% of the population is below that value for Z. And I could literally do this for any value of Z, from a very large value like 3.5 down to a very small value like -3.5. Okay, so, and we'd have the areas for this entire distribution. Well, if I go back to the distribution, when I look at this, one of the things that we know in statistics, when we're dealing in public health and statistics, is that we're very rarely going to have information about the entire population. We're usually going to be dealing with samples from the population. In other words, if we're going to be out measuring the levels of a hormone or a contaminant that's turning up in humans, and we're going to take blood tests, and we may not have the opportunity, certainly, to sample the entire population, but we may have to take a random sample from that population and hope that if we take a large enough sample, that we'll have a pretty good idea of what the true value is and what the true distribution is in the entire population. Okay, so we're dealing in a lot of cases with situations where we don't know what exactly this distribution looks like, but we want to take a sample from this distribution. Okay, so now I'm going to get a new page here. I'm going to redraw that here. Here is our population distribution. Okay, mean is 100. Standard deviation, again, mu represents the mean. for the population. Standard deviation is equal to 10. And I'm going to take a look at this, and I'm going to say to myself, well, let's say that I take a sample of size 25 from this population. Okay, if I take a sample of size 25, I'll be getting numbers from throughout this population. I might get 85, 92, 112, so on and so forth. I'll get 25 numbers that represent this distribution. More of them will be towards the center than towards the end, just simply because there's less likelihood of my picking someone out randomly that has a very low value or has a very high value, right? So now, since I don't really know this, I can't really, my eyes don't actually see this, right? That only exists in the real world, but I really can't see it. My only view of what's going on here is what I see in my sample of 25 people. Okay, so it's important for me to understand how sample distributions work. How, if I sampled this and then repeated that sample again, how reliably would I get a value that really approximates the mean of the entire population? And what we'll find is that if we repeatedly take samples of size 25, that we're going to get a new distribution, which is a distribution of all the sample means of repeatedly taking samples here. That's going to have the same mean as this is going to have. It's also going to be 100, right? Except that now, because I'm taking samples of size 25 and averaging them and making up a new distribution, that this is going to be a much narrower distribution than this one was. And if I took samples of size 100, right, those would even be closer to all the values being very close to the mean. So that would be even a narrower distribution, be less spread. So whenever I take these samples, I'm saying to myself, well, gee, my sample mean is approximating my population mean, but my standard deviation for all of the samples, the likelihood that that sample or the spread of those repeated samples, that's going to be much narrower than the spread for the entire population. Okay, and we know that that relationship is, and we call that standard deviation for the sample means, we call that the standard error. We know that that standard error is equal to the standard deviation of the population divided by the square root of the sample size. Okay, so in this case, size of a sample, in the case of a sample size 25, we know that, let's see, 25 square root of 25 is 5, standard deviation is 10. We know the standard error is equal to 2. So we know that 95% of the sample distributions should be between 2 standard deviations below and 2 above. That would be 96 to 104. If I did this again with a sample size of 100, this would be 100, this would be 10. 10 divided by 10 would be equal to 1. Standard error is equal to 1. So 2 standard deviations below would be 2, and 2 standard deviations above would be 2. So it would be, we'd expect 95% of the values to be between 98 and 102, right? So we can use this knowledge to help us understand what a sample of size n is telling us and how good it is at predicting the actual population mean. Okay, so we're going to move into now the first part of what we're likely to see on the exam. Okay, so you guys got that so far? Does that make sense? Everybody comfortable with that? Okay, good, good. All right, good. I figured we'd be okay with that at this stage.